A dielectric is an insulating material that when placed between the plates of a capacitor will increase the capacitance. Common dielectric materials include rubber, plastic, or waxed paper. C sub O represents the capacitance of a capacitor that has no dielectric material between its plates. K stands for a dielectric constant that depends on the materials being placed between the plates. And C then stands for the final capacitance once that dielectric material has been introduced between the plates. A formula we had used in the past for capacitance of a capacitor was A times epsilon naught over D. So when a dielectric material is involved, we'll actually just take that formula and we'll multiply it by the constant K. K depends on the material that's being used as a dielectric. Now, one way to create a very large capacitance for a capacitor is to shrink the distance d between the plates down really small. And that would be one way to get our charges really close to each other so that they exert a very strong attractive force on each other. This can cause a lot of charge to want to pile up on our plates. But in reality, unfortunately, there's a limit to how small the distance d can actually be. If the distance d becomes too small and the field between the plates becomes too large, then we can have an electric discharge between those plates. What will happen is we could have a dielectric breakdown of the air between those plates. And even with a material between the plates, we can still have a dielectric breakdown where a spark will allow electrons to jump from one plate to the other. This is a problem for capacitors. Let's take a look at the way that the molecules inside the dielectric will polarize inside the capacitor. At first, the molecules are randomly oriented in the absence of an electric field. But as the charges build up on our capacitor plates, they will introduce an electric field. That electric field tends to polarize the molecules of the dielectric that's between those plates. It'll create a torque on the molecules, making them rotate such that the positives of the molecules are pointing toward the negative plate, and the negatives of the molecules point toward our positive plate. This will have the effect of increasing the capacitance of the capacitor. It'll increase the maximum operating voltage that can be achieved. It can also have the additional benefit of supporting the plates and keeping them separate, so that hopefully no charge gets exchanged between them accidentally. Let's try an example problem. A parallel plate capacitor is constructed using a dielectric material whose dielectric constant is 4, and the dielectric strength is 1 times 10 to the 8th volts per meter. That's going to be the breakdown strength. So if the electric field becomes as big as 1 times 10 to the 8th volts per meter, unfortunately at that field strength, the dielectric material will break down and charge will be allowed to transfer right through the dielectric medium. Let's say the desired capacitance is 0.15 microfarads, and the capacitor is designed to withstand a maximum potential difference of 4,000 volts. Let's find the minimum area of these capacitor plates that will allow this to happen. All right, so first I'll draw my positive plate. And this time we have some material between our plates. And I'll draw a negative plate. We want a 4,000 volt difference between our plates. We want the capacitance to be 0.15 microfarads. We also see that our dielectric constant K is going to be 4. And we know the maximum field strength within the capacitor. It cannot exceed 1 times 10 to the 8th. If we take a look at our formula for capacitance, which would normally be A epsilon naught over D, we'll now introduce the dielectric constant K. That's what's different here. And we can plug in everything that we have so far. Our capacitance needs to be 0.15 microfarads. Our K constant needs to be 4. We don't know the area. Our permittivity constant is 8.85 times 10 to the minus 12. But unfortunately, we don't know the distance between the plates. But here we can actually do a little substitution using the formula delta V equals E times D. So if we were to solve for D here, we would find that the distance needs to be delta V over E. So I'll just take that formula and plug it in here. So we'll get 0.15 microfarads equals 4 times A times 8.85. And then we'll divide by delta V over E. Luckily, we have those two quantities. The delta V we see is 4,000. And the E is 1 times 10 to the 8th. So let's plug those things in now. If we solve this for A, we get 169,500 square meters. That's a very large area. So one of the ways that capacitors can be created with very large areas would be to roll them up such that one metal sheet here is in contact with our dielectric medium, and then we'll have another metal sheet that's in contact with the other side of that medium. So one of them is going to be the positive plate, and then the other one's going to be the negative plate. Okay. And then what we can do is actually roll it up like this. Okay. And so when we're all done, we'll have something which looks like a cylinder. But really, it's a tightly wound device where the positive plate is always kept separate from the negative plate, and a dielectric material between the plates keeps them nice and separate. Typically, simple devices that we would use in lab will just have a terminal here, which will be a positive terminal, And then on the other side, we'll have a terminal for the negative plate as well. So we can easily attach one wire to the positive plate and another wire to the negative plate.